Okay, I wanted to finish up section 9.4 here, which is the last section that we're doing for the course. We had done an example in the last video finding a unit vector. So we're right here now. Here's a definition. The unit vectors 1, 0, and 0, 1 are called standard unit vectors in the plane and are denoted by I and J. I talked about the position vector, which just simply means that you're starting at 0, 0 as your initial point. And so the terminal point of this vector would be AB. You can rewrite this as the sum of two position vectors, since you're just going to be adding components, right? A plus 0 is A, 0 plus B is B. Scalars can come out of vectors, okay, just as they can be distributed into a vector. So I've pulled out A and B to get these two standard unit vectors to appear. I is the vector 1, 0, and J is the vector 0, 1. So vector V is represented by AB. You can also write vector V using this notation, AI plus BJ. And that's a notation that your book chooses to use. I mentioned that a lot of books will have bold letters for representing a vector. If you're using the IJ notation, I and J will also be bold. Okay. So in this problem here, vector V, which is represented by the position vector -2, 5, and vector V, which is represented by -2i plus 5j, are exactly the same thing. It's just a notational thing, right? Both forms represent a position vector. All right, so let's take a look at an example here. Suppose that we have two vectors, v and w, and I'm using the ij notation, all right, which again is what your book chooses to use. We're going to find each vector and write your answer in the form of a position vector, AB, in either form, okay, the sharp bracket form or the IJ notation form. So part A, suppose that I want to compute 3v minus 2w. 3 and -2 are scalars, right? V and w are vectors, and a scalar can be distributed into the components of each vector. So I've done that. 3 times 3 is 9, 3 times -5 is -15. -2 times -2 is 4. -2 times 3 is -6. And so I'm adding these two vectors, which means I'll want to add the components. 9 plus 4 is 13. -15 minus 6 is -21. So this position vector here would be my answer. Or if you're using IJ notation, 13i minus 21j, that means exactly the same thing. Okay. Part B, we're computing a unit vector. Remember that how we get a unit vector is we take the vector and then divide by its length. Vector V is given to us here as the vector 3, -5. Let me divide by the length of that vector, okay, using the distance formula. I'm starting at 0, 0, right? So that would be the square root of 3 minus 0 squared plus -5 minus 0 squared, or that would be the square root of 34. 1 over root 34 can then be distributed into the two components, since that's a scalar. And so my answer then, this unit vector, would be the vector 3 over root 34 and -5 over root 34. Or here's what that looked like using the IJ notation. This vector, if you were to check, would have a length of 1. Okay. The next thing, suppose that we have a picture of a circle of radius 1, and I've got vector u, which is a position vector. I'm starting at 0, 0, and the terminal point is at some point on this unit circle here. Suppose that theta is an angle of inclination that we're using to produce vector u. Okay, now u is a unit vector, since I'm working with a circle of radius 1. And in this picture here, the terminal point of u would be represented by using coordinates x, y. Okay, and how you would get to that point would be start at 0, 0, go x units to the right, and then y units up. I've got a right triangle built into this, though, so of course I can use trig, right? Cosine of theta would be adjacent over hypotenuse. The adjacent side would be x. The hypotenuse would be u, but the measurement of u is 1, right? So x would be the same as cosine theta. Sine theta is opposite over hypotenuse. The opposite side would be y units. The hypotenuse has a measure of 1, and so therefore y would be represented by sine theta. So vector u in the position vector form would be the vector cosine theta sine theta, or cosine theta I plus sine theta j if you're using the ij notation. Since vector u is a unit vector, then vector u is equal to vector v divided by the length of vector v for some other vector v. Vector u is represented by cosine theta I plus sine theta j. So in this equation here, if you multiply both sides by the length of vector v, then vector v is represented by the length of the vector times cosine theta I plus sine theta j. In other words, what we're doing here is we're creating a formula. If you happen to want to find a vector and you know the length of the vector, and you also know the angle of inclination, okay, in the problem, you can find vector v by using this formula here. Okay, so I had just two examples that I wanted to work through in the book, and then I thought we'd call it good on the topic of vectors. I'm on page 622. Problem 76 is an application problem. Let's take a look at that. It says two forces of magnitude 30 newtons and 70 newtons act on an object at angles of 45 degrees and 120 degrees with the positive axis as it's shown in the figure. We're going to find the direction and the magnitude of the resultant force. That is, they want us to find the vector F1 plus F2. Okay, now they have this picture, right? And they've represented the magnitude, the lengths of vectors F1 and F2. It's 30 newtons and then 70 newtons. And we've also got the angle of inclination represented there in comparison to the x-axis. So I have redrawn that picture, and we want to find F1 plus F2, which is going to be a vector. And the plan here is to first find F1 and F2, and then once we have those vectors known, we'll just simply add those together. Well, they're telling me the length of F1 and the length of F2, along with the angle of inclination according to the x-axis. So in doing this problem, like I'd want to be using this formula here twice. Let's go ahead and do that. So F1 would be calculated by taking the length of F1, which is 30 newtons, and then I'm going to multiply that by cosine of theta is 45 degrees, I plus sine of 45 degrees, j. Cosine of 45 degrees, that'd be 1 over root 2. Sine of 45 degrees is also 1 over root 2. Distribute the 30 there, and you can rationalize the denominator. Also, 15 root 2i plus 15 root 2j, that would be the vector F1. Okay, now do the same thing, but with F2. Okay, the length of F2, the magnitude, is 70 newtons. By the way, there's two common systems that you would work with with vectors in physics. That'd be the SI system and then the US customary system. So currently we're in the SI system, which is what most of the world uses. The common measurement for magnitude of a vector would be newtons. Then, so the magnitude of F2 is 70 newtons, and the angle of inclination there is 120 degrees. That'd be my theta value. Cosine of 120 degrees is negative 1/2, since the adjacent side would be a negative 1. Sine of 120 degrees would be root 3 over 2. The opposite side is root 3. And of course, I'm working with a 30, 60, 90 right triangle in quadrant 2. Distribute the 70 there and simplify. So negative 35i plus 35 root 3j would be the vector that we're talking about there for f2. To get f1 plus f2, I would just simply add the two components then. 15 root 2 minus 35 would be the first component. 15 root 2 plus 35 root 3 would be the second component. Okay, and I'm using the sharp bracket notation. Of course, if you probably already noticed this. If you mean to refer to a vector, don't be using point notation. That's you've missed the idea. Then make sure you get either the sharp bracket notation or the IJ notation would also be fine. Problem 82 was the last problem that I had selected. Just another application of vectors, and so let's take a look at that one next. We want to find the weight of a car. It says that a magnitude of 1,200 pounds of force is required to prevent a car from rolling down a hill whose incline is 15 degrees to the horizontal. What is the weight of the car? Okay, so if you were to flip back in the book 2 pages here, they have a similar problem where it's example 9, and it says that 2 movers require a magnitude of force of 300 pounds to push a piano up a ramp inclined at an angle of 20 degrees from the horizontal. How much does the piano weigh? So they're very similar in the wording, right? You're wanting to find the weight of a piano, and in this problem we're going to find the weight of a car. Now, so I've got a picture drawn, okay? There's a car on the ramp, and I'm going to let F1 be the force due to gravity. That's what they're doing here in example 9. F1 is the force due to gravity. F2 is going to be the force required to move in this case, the car up the ramp. Okay, and F3 will represent the force of the car against the ramp. So they've got a picture drawn there, like I said, with the vectors also included. Now, in this picture, actually in the problem, we would like to know the magnitude of F1. Okay, F1 represents the force due to gravity. Okay, the magnitude of F1 would represent that weight. Weight is an example of force with with gravity figured in. Okay, so we'd like to know the weight of the car, like I said. Now, in this problem, I've drawn the vectors, and you'll notice that we have a right triangle here and another right triangle here. Okay, F2 is a vector that would be parallel to the ramp in direction, and then F3 is also a vector that would be perpendicular to the ramp. Okay, so I mean for this angle here to be a right angle, although I didn't mark it. I did mean for that to happen. Okay, also where F2 and F3 would meet, there's going to be a right angle also. Okay, since F2 is parallel to the ramp, F3 is perpendicular to the ramp. Now, in this bigger triangle, we have a right angle, and of course F1 is the force due to gravity. That's what's pulling the car down to the ground, straight down vertically. So I've got a right angle here. Here's a 15-degree angle. The third angle in this triangle would be 75 degrees then, right? Since if I take 90 degrees plus 15 degrees plus 75 degrees, I'd get 180 degrees. The sum of all 3 angles in any triangle is 180 degrees. Now, I mentioned just a moment ago that this angle here, although it's not marked, would be a right angle. So if I know that, by splitting this right angle into 2 angles, the angle measurement here is 75 degrees. The other angle measurement here would be 15 degrees, and I've got that marked. That's 15 degrees also. F3 and F2 are meeting at a right angle, and so that third angle down here would be 75 degrees. since if I add all three angles together in this other right triangle, I would get 180 degrees. Basically, the thing that you'd want to observe here is that these two triangles are similar triangles. Okay, you just got a scaled up, scaled down version of one compared to the other. Now, in the problem, we would like to know the magnitude of F1. The magnitude of F1 represents the weight of the car. In this triangle with the vectors formed, I have a 15-degree angle up here. Now, the magnitude of F2 is 1,200 pounds. Okay, they had told us in the problem that a magnitude, let me just bring it back up here again, a magnitude of 1,200 pounds of force is required to prevent a car from rolling down the hill. All right, so that would be the magnitude of F2, like I said. That's going to go in the, or that's going to be figured in. And I need to find the magnitude of F1. Well, if I'm working with this 15-degree angle, F2 is opposite that. F1 would be the hypotenuse in this right triangle here. Opposite over hypotenuse means that I got to be doing something with the sine function. So I've got that set up. Sine of 15 degrees is opposite over hypotenuse. The opposite side would be the magnitude of F2, which we've already said is 1,200 pounds. And then you're dividing that by the magnitude of F1, that'd be the hypotenuse. If you solve this then for the magnitude of F1, 1,200 pounds divided by sine of 15 degrees, you want to make sure that you're in degree mode with your calculator. I'm getting roughly about 4,636 pounds would be the weight of this car. And you know, that sounds right. That would be a very normal weight of a car. Okay. In fact, it is the right answer, right? But so anyway, that would be how this problem goes. All right. There are several applications of vectors that you'll see in calculus and in the calc sequence. You do a lot of things with vectors in Calc 3. In fact, so you'll look at plenty of applications there. So this is just a very brief introduction into things later down the road, but hopefully that's somewhat helpful. All right, we are now done with what I wanted to cover in Chapter 9. So the homework in 9.4 is on page 621. Be sure to look at those problems for me.